Good afternoon, everyone. Hi there. Hi, Tanisha. Hi, Ultimate. I'm just going to give people a few more minutes to arrive. Welcome if you're joining us for the first time. This afternoon, this is going to be the Snap Revised GCSE Physics Introduction to Forces session. Again, just give you a few more minutes for a few more people to arrive. Hi, folks. Hi, Ben. Hi, Nisha. Hello, Callie again. Right. So it's been a minute, so let's press on then. So just by way of introduction, in case you're watching and you haven't been to one of my physics sessions before, I'm David. I'm a physics teacher of 16 or 17 years experience and teach A-level and GCSE. Hi, Natasha. So we are covering the content for all of the UK specifications. That's AQA, Edexcel, OCR. I do get asked quite often if we do IGCSE content, and we don't specifically cover IGCSE content. It's a little bit different. Today, we're going to be looking and talking about forces. Hi, Evan. And specifically, we're going to be looking at pushes, pulls, forces. Sorry, let's go back to my slide where I'm going up. Basically an introduction, a basic introduction. We're not going to be looking at velocity time graphs or anything like that. So you can subscribe to our tutoring service, and the tutoring service kicks off next week. For that, you get 3 or more classes per week. You get a full curriculum coverage for all of the exam boards, as I've said. Hi there. And you get access to all of the handouts and also a library of the past recordings, and also one-to-one drop-in tutoring. When I say one-to-one, you get very small group tutoring support. So you get the opportunity to have one-to-one question sessions, question and answers with qualified tutors. Hi, Anushka. So there is a code you can use to currently get a couple of weeks free trial. Now that free trial code expires on the 9th of March. So if you would like to have a couple of weeks trial, you sign up on the Snap Revised website. The link is there on the screen in front of you now, and you can also download the slides. And that will give you, as my colleague is saying in the chat, a 2-week free trial. So don't forget to use it before the 9th of March because it expires on the 9th. Okay. So what we're going to be looking at today are forces, identifying forces, contact forces and non-contact forces, and also talking about and understanding the difference between scalar and vector quantities, and understand the force and how it is a vector quantity and why force is a vector quantity. Hi, Dhruvi. Magnetism, we covered a little bit in the drop-in session 2 days ago. If you have any specific questions on magnetism or topics that aren't covered in today's session on forces, then please, Dhruvi, and anyone else who would like to, please pop into a drop-in session next Tuesday, which will be at 5 p.m. next Tuesday, if my memory serves me right. Have a look at the schedule on the Snap Revised website and on their YouTube site, and you can see what's coming up in all the subjects that we offer. Hi, Anushka. Okay, so examples of forces, contact and non-contact, difference between scalars and vectors, and how force is a vector quantity. Khadija, hi there. And so the AQA points, just understanding what contact and non-contact forces are, knowing what a scalar and a vector quantity is, giving examples of non-contact and contact forces. And hi, Dana. And essentially, the Edexcel and the OCR specifications cover the same points. So recalling what vector and scalar quantities are, being able to identify each of these ones as either vector or scalar, describing contact and non-contact forces, and we'll talk about the differences between the two in a moment. And the OCR spec points, again, the same things essentially, so non-contact and contact forces, etc. So we will cover the content for all of those curricula today. Nima, there are maths drop-in sessions, I believe. Have a pop over to the Snap Revised website and the YouTube site for Snap Revised and have a look at the schedule. I'm sure you'll find what's coming up there. There's a list of future live streams to come. Right, so let's have a look at what we already know about forces and types of forces. So to start with, what do we know about the difference between distance and displacement and speed and velocity? Let's start by talking about distance. If we were asked to define distance, what would we say? Uh, Talia, drop-in sessions are where, rather than being focused on one topic like we are now, we have a spread of topics and we're a little bit more open to being led on different topics if you've got particular questions. Yes, you can, Dhruvi. Yeah, you can see a schedule of upcoming live streams and download the library of recordings when you joined on the website as well. So what do we know about distance? How would we write a definition of distance? Thanks, Nisha. So the measure of one object to another. Distance is, Dana, a measure of how far something is. Yeah, how far something is away from us. So, okay, so it's the amount of space between 2 points, I think is a summary of that. Amount of space between 2 points. Amount of space between 2 points. What do we measure distance in? Nice straightforward question. What's the unit of distance? Thank you, Evan. Thank you, Talia. I hope I'm pronouncing your name correctly. Thanks, Nisha. So measured in meters. Quite correct. And what's a typical thing we can measure distance with? Believe it or not, you will need to perhaps say this in an exam question answer. So what might you use to measure distance in a laboratory? Thanks, Drudy. It could be a kilometre. The K just means times 1,000. And thanks, Evan. Yeah, ruler, tape measure. Are the typical things you would mention if you're asked how you would measure a distance. Be sensible if you're measuring a distance between you sort of making a sound to measure an echo coming back or something. You wouldn't get a 30 centimetre ruler to measure a distance to a big wall, so use tape measure, but not a major point. So it's the space between 2 points measured in meters. 1 meter is how many centimetres? Thanks, Talit. How many centimetres is in 1 meter? Great, thank you. So 1 meter is 100 centimeters. And how else can we write 1,000 meters? Just a quick reminder. Thank you, Asiya, Anushka. And 1,000 meters we can write in some other way. Yeah, thanks, Evan. So 1,000 meters is 1 kilometer, and the K means times 1,000, just a reminder. Okay, so that's distance, just the general amount of space between two places. Importantly, not necessarily in a straight line. So now we move on to speed. How can we define speed? If you were just asked to describe what speed is, what is speed? Brilliant, thank you. Thank you for those other answers, S and Floss. Evan, thank you. Dana, Asiya, yep. How fast something is, the rate of change of distance, yep. Oh, Master Yoda, how long it takes to get from one place to another? That would be a time rather than a distance. How fast an object moves, yeah. So very simply, we'll just say how quickly something is traveling or moving. That's what speed is, how quickly something is moving. And Evan's already said that speed is equal to distance divided by time, which is absolutely correct. So we put that there as well, distance divided by time. And if we look at the whole journey of something from beginning to end, and we time that journey, and we do the distance divided by the time, what we end up with is the average speed, because we're taking into account the whole time of that journey. We measure speed in what unit? I can see the boss has given some answers there. Of your 3 answers, the boss, or anyone else would like to say, which is the SI unit, the generally used SI unit of speed? Thank you, Talia. It's meters per second. Ben, we can use kilometers per hour. It would be pretty mean of an exam board to do that, but if they did, you'd have to remember to convert the hours into seconds and the kilometers into meters. So it's meters per second. And Floss, that's a brilliant question. I'm going to come to that in just a second. So the unit is meters per second there. And is it the same as velocity? No. So speed is not the same as velocity. Speed is how fast something is going generally. It doesn't take into account direction, and it doesn't take into account sort of changes in speed. If you like, if you do a standard calculation of speed using an overall distance and divide it by the time taken, then you're only going to get an average speed. Velocity is a more precise measurement of how fast something is going, but also in a particular direction. So we're going to come to that. Yes, velocity is directional. Dana, velocity does have magnitude, but it also has direction, whereas speed only has magnitude. Okay, we're jumping ahead a little bit here, so I'll move on. If anyone's got any questions, just pop them into the chat. Okay, so let's go to forces for a bit. We'll come back to speed and velocity in a moment. So what would you say defines a force? What is a force? If you were asked to describe what a force is, what would you say? Thank you, the boss. Thank you, Asia. So a force is a push or pull, not quite pressure, because pressure is force divided by an area. So that's something slightly different. Force is something which may act upon an object. Yeah, master. And strange calling you that. Push or pull is certainly two things you could call a force. There's one other thing you could describe a force as. So a push, a pull, or what else could you do to an object which might not be quite as simple as a push or a pull? Hi, Rama. Hi, Hannah. You might not immediately come to mind, but it's a push, a pull, or yeah, that's a good definition, Josie. That's good. An action that changes the size, shape, or motion of a body. I'm going to add or a twist to what a force can be. So a push or a pull or a twist, something which changes the shape, size, or direction of an object is really good. Changes shape, size, or direction of an object. Good. Okay, so yeah, a stretch, a twist, a pull, a push. These are what you would say if you were asked to define a force. So if we've got something going on, if we've got a hand pushing on a box here, we've got the hand pushing in the direction the arrow is going there. What's the box going to do if you're pushing in the direction I've just drawn the arrow on? Hi, Yassine. So we're pushing on that box, we're applying a push force in this direction. The box is going to do what? Okay, yep, move to the right. So box moves right. It will accelerate to the right. And the box actually pushes back on the hand with exactly the same magnitude of force as the hand pushing on the box. Okay, good. Yeah, it will accelerate until forces are balanced again. So until opposing forces like friction and air resistance match the pushing force. Good. So let's look at now contact and non-contact forces. Can we have the definition of a contact force? So what is a contact force? And what are the conditions for something to be called a contact force? Thanks, boss. So we've got contact force is a force between objects that are, physically touching each other. Let's have a look what Hannah said. By Newton's first law, will move at the same speed. Ooh, be careful there. Can't really go into that one right now, but I might have time later, Hannah. Touching forces that require contact to occur, direct contact, yeah. So a contact force is a force between objects which are physically touching. Just to avoid saying in contact again, because it comes in the definition. There we go. So a force between objects which are physically touching, that's what a contact force is. And a non-contact force, fairly straightforward, I hope. What would you say to describe a non-contact force? Nisha, that's a perfectly good explanation. And Yoda, the box pushing back is an example of Newton's second law. Third law. Sorry. So any force will result in an equal and opposite force pushing back in the opposite direction of the same magnitude. So with non-contact forces, thank you, Yanatul, and S not touching. So a force between objects which are separated, I'm just going to say. I hope I'm going to spell it right. Okay, force between objects which are separated, and we'll talk a bit more about them in a little while. Okay, so contact and non-contact forces. Let's give some examples now. Let's see what we can come up with. So can we name some? Hannah's jumping the gun there and coming up with some answers already. Brilliant. So usually the force is applied via a matter of field. So yeah, non-contact forces Hannah's talking about, magnetic, electrical, or gravitational. In fact, she's pretty much there, Hannah. You've summarized them all. So non-contact forces, we've got gravitational forces. We've got electrostatic forces, forces due to electric charge building up on surfaces. They're both non-contact, and Hannah and Dana have also said magnetic fields, so magnetic forces as well. And they're the only three non-contact forces that I can immediately think of that you need to be aware of, that I believe exist. They're certainly the only ones that are examined. So gravitational, electrostatic, and magnetic forces. What about contact forces? Can you name a few different examples of contact forces where objects have to be in contact? Yeah, drag would be a contact force, because drag is where particles of liquid or fluid or water or the air, whatever, are striking an object moving through it. So drag would be a contact force. Another one would be, let's have a look there. Yeah, I'm going to put a slash up thrust next to drag because they're not dissimilar. They normally act in different directions, I realise. Friction, brilliant. That's a good one. Friction's a good contact force, probably one of the best ones to come up with early on. Friction. Thank you, Asir, for reaction force. So a reaction force is the force that reacts to a force acting on a body. So it's often called a normal contact force. So if I put a box on a table, this is going to be a terrible drawing here because it's too small. If I put a box on a table there, the box's weight is acting down, but the table is pushing upwards with a force exactly equal to the weight. And that's called a normal contact force. Let me just delete the M that I've actually put there at the beginning of normal. So a normal contact force, same thing as a reaction force. We've got drag, we've got also people are saying air resistance, that's a good one. Again, form of drag. No one said tension, so tension in a rope is another good example. Now, quite a few of you are coming up with examples of energy here. I've got nuclear, and I think I saw heat in there as well. So they're not non-contact forces, they're examples of types of energy. And lift would be a contact force because it's to do with gases, gas pressure. So yeah, it would be to do with the net pressure underneath a wing of an aircraft being greater than the pressure above. So we've got tension, air resistance, normal contact force or reaction, friction, drag, upthrust. Brilliant. And the non-contact forces, I think you all came up with really quickly because they're far fewer in number. Okay. Right, so let's look at some examples. Let's think about the forces that are acting on our parachutist there. So we've got someone who has been skydiving, they've opened the parachute. What is the force acting? Well, there's several forces acting here. Name a force acting on the parachutist. Air resistance and gravity. Right, okay, so gravity causes the weight, which direction is the weight acting? We'll definitely come to air resistance next, Khadija. Thank you, and Dana. And thank you, Khadija, for the clarifying which direction air resistance is acting in. Dana, thank you, and the boss, thank you. So the weight is acting downwards. Just want to make the distinction. You can normally get away with saying gravity or weight, but really gravity is the thing that gives rise to weight. Gravity is a field and weight is a force. So they are a bit different, but the examples let you get away with saying gravity quite often. So that's the weight, or giving rise to the weight pulling down. And we've already said that air resistance is acting in an upwards direction. Okay, and well, how would you describe the speed of the parachutist if the air resistance upwards was equal to the weight downwards? What word could you use to describe the speed of the parachutist? Constant speed. Yeah, brilliant. So these two things, when they're equal or balanced, the parachutist is moving at constant speed. So when they're equal and opposite, the net force acting on the parachutist is 0. So they're not accelerating, they're not speeding up, they're not slowing down. Okay, brilliant. Okay, so there's our parachutist. What about the car? The car, you might come up with a few more things. What forces are acting on the car? So on the car, right, brilliant, thanks Donna. We've got the friction of the wheels. I'm going to draw that there. Friction and a little W there. So we've got friction at the wheels where the tires meet the road. Where else have we got some sort of friction as the car's moving? Thank you, Donna. That's brilliant. You've described the weight. So we've got the weight going downwards from the car's center of gravity. So the weight down. And you've also mentioned the normal contact force, which is going upwards, which we hope equals the weight. Otherwise, you've got a problem. You've got a floating car or a sinking into the road, right? Normal contact force there, friction going backwards. And thank you, Lowell. We've got air resistance. Yeah, so air resistance is also working if the car's going forwards. It's also working in a reverse direction. It's trying to slow the car down. So air resistance is acting there. It's a type of friction, if you like. But air resistance is another important force acting on our car. We've got our weight going downwards, and yeah, we've got the engine thrust forward. So we've got the engine forces, which I'm going to call thrust, as you would with an aircraft or other things as well. So you've got the engine, the thrust or the forward force due to the engine of the car. Yeah, brilliant. So I think we've covered them all there. Don't think we can think of any more. So that's good. So we can think of and name and hopefully label up forces acting on different objects. So how are we feeling about that so far? We've just covered what speed is, what distance is, and then we talked about contact and non-contact forces. And also we thought about a couple of different situations. So if I could have some 1s, 2s, and 3s, that'd be brilliant. Thank you very much. So people confident looking so far. Any particular questions on anything? I know this seems very straightforward probably to a lot of you, but some of you, some aspects of this might be new to you. Some of the words, things like normal contact force, they may be phrases you've not come across before, so don't worry if that's a problem. You'll soon get used to those and use them happily. So, okay. Thank you, Ultimate. Right, brilliant. So lots of 1s, just the 2 there. But if you've got any questions, there'll be time later to come back as well. Okay, let's have a look at a few questions. Thank you, Robin, as well. And Josie and Janital. A few names I've not seen there before. Okay, 4A1, which of these forces keeps the moon moving around the Earth? So the boss is saying C. Do we agree with the boss? Is it a contact force? Is it electrostatic force? Is it magnetic, or is it gravitational? Yeah, brilliant. So you're all coming up with C, people who are putting their answers in the chat there. Yes, Hannah, is the force that acts on an object to pull it into circular motion called a right? Centripetal force is a force which causes something to move in a circle, but you wouldn't replace the name of the force necessarily with centripetal force. I'm trying to describe this clearly. It's quite hard, actually. Centripetal force could be caused by friction. If you've got a car going around a roundabout, then the friction of the tyres against the road surface provide the force towards the centre. So friction provides the centripetal force. With the moon going around the Earth, the centripetal force to keep the moon moving in an approximately circular or elliptical orbit, that's gravitational force providing the centripetal force. With electrons orbiting the nucleus of an atom, it's electrostatic force providing the centripetal force. So if you see what I'm trying to say, the centripetal force always has another name as well. It'll be something. If you're whirling a conch around on a string, the centripetal force is the tension in the string. So you don't actually call it that on its own. Thank you. I'm glad that makes sense. It's sometimes tricky to explain that. Okay, yeah, good. That's what I was trying to say. Light, yeah, it's the name for a type of force. Right, let's move on to the next question. I hope you can see this one clearly. The text is a little bit smaller on this one. So we've got racing car teams track the progress of cars to analyze their performance. One team was testing how well a car accelerated at the start of a race. And here are the forces. So we've got reaction force or normal contact force. We've got the driving force we talked about. Counterforce would be friction plus air resistance. It's a slightly odd thing to call it. I would say don't call things like that counterforce. Might be a slightly older question, this one. And then we've got the weight acting downwards. Draw a line from each force to the correct description of the force. So the counterforce, okay, that's what I've done it, sorry. So the counterforce here in this question here, what's causing the counterforce? Yeah, thank you, Ultimate. So we've got counterforce due to friction and air resistance there. And then driving force is coming from what? Where's the driving force coming from here? Push of the engine, thank you. Brilliant. And then the reaction force going upwards. So we've got push of the engine for the driving force. And then the boss has written 1B, 2A, 3D. Force from the ground. Yeah, Ultimate as well. Thank you. Thank you, Hannah, too. Yeah, so the reaction force is the force from the ground on the car, which leaves us the weight being the pull of gravity on the car. Okay. Are you all happy with that? I'm guessing so. Okay. Fantastic. So another question here. We've got a boat pulling a water skier through the water. And here we've got a little arrow there, which is representing the thrust from the propeller of the boat. The arrow there represents the force on the water produced by the engine's propeller. And the force causes the boat to move. So can we explain why does the force from the propeller pushing backwards on the water make the boat move forwards in the opposite direction? So this is to do with one of Newton's laws again. So the resultant force is forwards. Doesn't quite explain it, but there's no harm in saying it if it helps you get to the answer. The resultant force is forwards, but that doesn't explain it. So we haven't quite answered the question yet. So if the propeller is pushing on the water backwards, what's the water? Thank you, Ultimate. You're getting there. What's the water doing to the propeller, which is attached to the boat? So the propeller pushes the water backwards. The water has to do something in reaction to that. So Dana, reaction force caused by the water because Newton's law states each force has an equal balance force in the opposite direction. The water pushes the propeller forwards. Brilliant. Hannah, when the propeller pushes on the water, it reacts. But yep, we're getting there. We're getting there. Great. And thank you, Ultimate. Yeah. So the water being pushed backwards causes the water to also produce. So the water produces an equal and opposite force forwards. Terrible handwriting, sorry. Okay, so and that's the force that pushes it forwards. And we've said the resultant force is forwards, the water produces an equal and opposite force forwards. That would be fine. Brilliant. Okay. Any questions on that one? We're okay on there. We can come back if you have any queries in a bit. So let's move on to section 2 then. Section 2, we're going to talk about vectors. So we started off talking about speed and distance, and they're examples of scalar quantity. So a scalar quantity has certain properties. If we were going to describe very simply what a scalar quantity is, what would you say? So what would you state a scalar quantity is? So quantity which, and Hannah, Dana, Sia, thank you very much. Not quite Janital. Scalar quantity is the one that doesn't have direction. So scalar is the simpler kind of quantity. It just has a bigness, a magnitude, a size, but it doesn't have direction. So a scalar quantity is a quantity which has magnitude only, which is magnitude. This word magnitude, it kind of means size. It has a number, it has a bigness, which isn't really a proper word, but you know what I mean. It has a bigness, it has a size, just a magnitude, it doesn't have any direction. Whereas, as all of you are jumping ahead and saying, it's brilliant. So vector is a quantity with both magnitude and direction. So a vector quantity is one which has magnitude and also direction, has magnitude and direction. Now, something that sometimes I've seen students get a little bit tied up with is when they're dealing with vector quantities in an exam question, they've got to state both the direction and the magnitude of a vector quantity. People aren't always sure how to discuss and describe direction. So the direction, you could say, you can say really simple things like up, down. You could say to the right, to the left. You could use north, south, east, west. Okay, it all depends on the context of the question. So if you're asked to state the magnitude and direction of a vector quantity, take your cue from the question and use whatever is sensible to easily describe the direction. Amjad, is current a scalar? Doesn't it have direction? Okay, not really, no, because current, no, current is a scalar quantity. Sorry, yeah, it's a scalar quantity. Although it has direction going around a circuit, it's the movement of charge, and the actual movement of electrons in wires is quite random. They jiggle around and go forwards and backwards quite a bit. It's just that the overall motion is in one direction when there's a current. So no, current is a scalar quantity. And Hannah's saying the fact that velocity is a vector explains why a car that moves in circular motion about a roundabout at constant speed is actually accelerating, since its direction is changing. And that is absolutely spot on. Yeah, by definition, if something is turning in a circular path, even if it's moving at constant speed, it's accelerating because its direction is changing. And velocity is a vector quantity. So it's not just the size of the speed, it's also the direction of the motion. So that's absolutely right. Energy is a scalar quantity. Thanks, Bohemian. Energy doesn't have direction, can be directed, it can be applied, and it can be, work can be done to transfer energy, but it doesn't have direction as such. Okay, so let's have a look at these two cars that we've got on the right hand side. What can we say about the speed of these two cars? Just going to write speed with a question mark. What can you state about the speed of those two cars? Give me a fact about the speed of these two cars. They are traveling at equal speed. It's the same. Thank you, Yoda. Thank you. Yeah. Thank you. Jan Nuttall has gone a little bit further by giving me directions, so we're coming to that. So they are traveling at the same speed. just want to pick up on something I've just noticed in the chat there from Hannah. Hannah's saying deceleration is the rate at which velocity decreases. That's correct. That's good. Prakriti, sorry, I'm sorry, I'm difficult with some names. Deceleration is basically the informal way. It's the opposite of acceleration. So deceleration is negative acceleration. Okay. And then, yeah, so the speed's the same, but the velocity is different. Okay, so they have opposite directions. So the velocities differ. Okay, different velocities because of different directions. Right, so let's move on to some examples then. So let's, we've already had one or two examples, so you can quickly reel them off again. Some examples of scalar and vector quantities. So think about some quantities you might measure or talk about or use in calculations that are scalar, that have no direction, and some that do. So mass is a scalar quantity. Time. So there we go. If you could just state whether you think they're scalar or vector. So ultimate's got mass, energy. We talked about speed. Brilliant. Distance. These are all scalars. Yeah, temperature, that's a scalar quantity. And there are many, many more. Let's think about some vector quantities now. So just to make it easier, let's just concentrate on vectors. So thank you, Hannah. Yeah, mass, time, energy, speed, distance. I wouldn't quite agree with Arbin there, Arbin. An example of a vector SI unit is the Newton. So forces are always vector. And then here we have momentum. Momentum is a good vector quantity. Momentum, which is mass times velocity. And then we've also got velocity there as a vector quantity. Yeah, force, acceleration. Gravitation is a type of force, so gravitational force would be a vector. Displacement, brilliant, thank you. Yeah, displacement. Let me just talk about a few of these before I move on, in case there's a few words there some of you haven't come across. Momentum, mass times velocity. Whenever you multiply a vector quantity by a scalar quantity, your resultant quantity is going to be vector. So if there is a vector quantity involved in a calculation, then what you have is something that has direction when you've calculated your answer. And displacement is similar to speed, but distance, but displacement is distance in a given direction. Work done is force times distance, so work done would be a vector quantity. You do work in a specific direction, and for work done, that direction is the force in the direction of application of the force. Pressure, force divided by area. So yeah, pressure, we could go on, yeah. Pressure, force divided by area, so that would be vector. Pressure has a direction, usually normal to the surface of a container. Okay. How do you know if it's scalar or vector? Experience, practice. If something can be, if you think logically about whether something can be directed in a particular direction, it often comes to mind quite easily. So time, you can't change the direction of time, arguably. So time is a scalar, there's a scalar quantity. I'll add it on the bottom here. Whereas something like a force, if you're pushing on something, you can imagine quite easily, I think, that you can make that force go in different directions. So anything you can direct will be a vector quantity. So weight is a type of force, which is why I haven't written it separately, but not mass, of course, because mass is not the same as weight. Yeah, brilliant. Thank you. That's right, Hannah. Yeah. So, for example, displacement written as 100 meters, and then you give a direction, so north. Yeah. So you'd give a distance and then direction. Fantastic. Energy transferred. Yeah, I know what you're saying, Ultimate, but work done on an object does have a specific definition, which is it's force times the distance moved in the direction of the force, but I do understand your point. I do understand your point. And actually, to summarize that one, you're not going to be asked to say whether work done is scalar or vector in any exam question. But because you are multiplying a force by a distance, technically it is a vector quantity. Okay, right, let's move on. Right, so force is a vector. So it's a vector quantity because you can direct it. I've just said this, you can direct it, can't you? So it can be a push or a pull. We've already said that. So the push or the pull or the twist is directed. Oops, sorry, let's get rid of that. So the push or the pull is directed. Okay, it has magnitude and direction. You couldn't really describe a force unless you gave a direction. It'd be quite hard to anyway to describe a force to somebody else, both direction and magnitude. Hi, Mr. Dan. Okay, so the parachute is there. Just a quick recap. The two forces acting on the parachute is downward and upward. We've got the downward force, which is, and the upward force, which is called something else. So we have, this is a vector quantity, the downward force, and that's weight acting towards the center of the planet. And then, thank you there, Evan, we've got air resistance, which is a force, therefore it's also a vector, and that's acting in the opposite direction to the weight, acting upwards on the parachute is there. And then we've got a magnetic force going on here. Is this an attraction or a repulsion? Is this magnetic force an attraction or a repulsion? Magnetism, north to south poles, attraction, brilliant, thank you. So we've got that pole being pulled that way, this pole being pulled that way. And just to go back to the parachutist, are these forces on the parachutist contact forces or non-contact? What about air resistance, contact or non-contact? Air resistance, contact or non-contact? Air resistance is contact. Okay, so air resistance is a contact force because although you can't see the air particles, it's air particles colliding with the surface that are giving rise to that force. So air resistance is a contact force. It's a contact force. The weight is due to gravity, so that makes it a non-contact force. It's easy to see why people might think that air resistance is non-contact, because I think it can be, because you can't see the air particles. It's probably quite easy to think, oh, it's just happening because there's nothing actually there. They don't have to touch, but they do. The air particles have to touch the parachute. Okay, and the magnetic force, is that contact or non-contact? Yeah, Tamana's given us the answer there, and the boss. So this is a non-contact force. Someone had a question there, but weight is contact. Weight, the reaction force to weight is a contact force, Dhruvi. So if you're sitting on a chair, the force you feel pushing back up on you, the reaction force from the chair, that's a contact force. But your weight pushing down is actually the non-contact force due to gravity. And the last one, where we've got a tug of war, we've got two people pulling in opposite directions. We talked about names of various forces earlier. This is tension, and is that contact or non-contact? Tension, force and contact, Asiya. Thank you very much. Brilliant. Okay. So let's move on from there. So here we've got an example of someone lifting weights. She's standing on a surface, otherwise she looks like she's floating in the air there. Let's put the car on a surface as well. There we go. So let's just whiz through these ones. Starting at her center of gravity, going downwards. Sorry, that's supposed to be a vertical line. What do we call the force acting directly downwards from the center of gravity of this person? Weight. Yeah, brilliant. And then someone's already mentioned we've got the normal contact force going up, which will be equal and opposite to the weight. I've drawn the arrow slightly long, but normal contact force. And then what's acting on these? These have their own. I'm going to go on and label this one, I think. So the two weights either side also have weight due to gravity. So that's acting down. So this one's going to be her weight plus the weight of the weights that she's lifting as well. And the normal contact force will add up to be equal and opposite to her weight plus the weights that she's lifting. Okay, I think we've covered enough with the car, to be honest, because I think we're repeating ourselves at that point. So how happy are we with labeling contact and non-contact forces and describing forces acting on different objects? If I could have 1s, 2s and 3s, that would be brilliant. Oh, Amjad, they have moment as well. The weights, yeah, they will. If you've loaded up your bar properly, you should have the same mass on either end so that you're not twisting your spine and your back as well. So they should be equal mass on each end. So the resultant moment is 0. Right, 1, 1, 1. Everyone seems fairly happy there on the side. Good. Yeah, and the moment is the turning effect of a force. Absolutely right, Hannah. Okay. So I'm going to be finishing a little earlier today in about 9 minutes time, just to make sure that the next session starts on time. So we have just a couple of exam questions to look at. Oh, Tamana, I can go back to any questions, however. So Tamana, the force acting upwards there was the normal contact force or reaction force. And that is equal to the sum of the weight of the dumbbell she's lifting plus her weight. Thank you, the boss. Okay, let's go back to our exam question. That one's rather, no, we can probably do this one quite quickly. Let's have a look. So a water tank is dripping water there. Scientists use 4 quantities, or could use 4 quantities to describe the movement of water drops. 3 of them are vectors and 1 is scalar. So which one is scalar? So we've got 4 different quantities we could use to describe the water drops. Is acceleration scalar? Is force scalar? Is mass scalar? Is velocity scalar? Which one's the answer? And we've got mass, mass, mass. Brilliant. Correct. So yeah, mass is the scalar quantity. So there are 2 forces acting on a ball as it falls through the air. The weight is shown on the diagram, acting downwards. Draw and label an arrow on the diagram to show the other force acting on the ball. So if the weight is acting downwards, what other force will be acting on the ball? Thank you, Donna. Air resistance, which is going to act upwards. I'm just going to draw it as an arrow going upwards. It doesn't really matter where you start the arrow. Technically, it's probably better to start it at the bottom of the ball, but it doesn't really matter. People aren't normally concerned with that. So it's an upward force due to air resistance as the ball falls through the air. Good. Let's have a look at another one. We've got 2 students studying the motion of a model train on a track, and they need to make distance and time measurements. To calculate the swim speed is 5 and its maximum velocity is 5 meters per second. What's the same about both of those quantities? What's the same about both of those quantities? So maximum 5 meters per second, maximum velocity is 5 meters per second. What would you describe as being the same about those 2 quantities? Thank you, Janatul. Magnitude, yeah, brilliant. So the magnitude is the same, they have the same size, the same number. What might be different? Yeah, they both have a magnitude of 5 meters per second, and you would use the same units, yeah, but without direction, that's speed, not a velocity. So the difference between them, what could be the difference between them, is the direction could be different, yeah. So the direction may differ. or you could just write direction. Direction is fine. Yeah, correct. Speed doesn't have a direction. Speed is just how fast something is going in any direction, whereas velocity is speed in a stated direction, being a vector quantity. Okay, one more exam question here. So this picture shows a man pushing a box, and we've got some of the forces shown. We've got C, B, and A, and D there. Which of those letters is friction? Friction. Which of those forces, A, B, C, or D, is going to be friction? We've got a lot of D's. We've got an A going there. So we've got 3 D's and an A, another D, a D. Okay, in this case, the clue is that it's normally shown at the junction between two surfaces. So friction is D. Okay, friction is a contact force that happens where two surfaces are in contact. Write down the letter of the force due to gravity. So gravity now we're looking at. Okay, gravity, we've got a couple of A's there. I think we can agree that the A would be the weight, which is the force due to gravity. So you're quite correct. That's going to be A. And the letters of the two forces that are an interaction of forces between two objects, so an interaction pair, which is the Newton pair there. Thanks, Ultima. Take care. And thank you very much. And hopefully see you next week. So which two are going to be an interaction pair? It's going to be B and C, as Sia has said. Kyvan, if you look at the link in the chat, I think my colleague might put up another message at the end as well to say where you can download them, but also the Snap Revise website or the YouTube channel, you can download the recorded stream. So B and C, either order, brilliant. For the last answer there. Angry, of course you can. I'm going to be finishing in a few moments, so another few minutes left. Okay, so let's do one more question. So here we've got the moon and the earth experiencing an interaction force that attracts them to each other. So we've got force P and we've got force Q. The object the force acts on. So what is force P acting on? Complete the table about these forces, right? Either earth or moon. So force P is acting on what? Force P is a force which appears to be away from the earth. To the right. So it's a force going to the right. It's interesting. It's interesting. I know why you're saying the moon, because you all know that the Earth, being much larger than the moon, supplies the gravitational force which keeps the moon orbiting the Earth. You know, if it was the other way around, and the moon wouldn't be the moon, we would be the moon of another larger body. So we've got a smaller mass called our moon, which is orbiting our planet. But nevertheless, the moon does exert a force on the Earth. And to remind you of that, think about tides. The reason we get tides is because water's being in the oceans is being pulled around by the gravitational force from the moon, and also to a lesser extent the sun, because it's much further away. So the object the force acts on, force P, is acting on the Earth, and it's pulling the Earth towards the moon. We have a pair of forces here, a Newton 3 pair. Yeah, it is the Earth. It is the Earth, and there is an equal and opposite force, which I think we've just sort of come out with in that last discussion, which is acting on the moon. So force P is exerting. Sorry, the force P is being exerted by the moon. Okay, so the moon is pulling the Earth towards it, and there is similarly a force that is pulling the moon towards the Earth. So force Q. Which object is force Q acting upon? So force Q is acting on the moon. Thank you, Dana. I capitalized the moon. It sounds pedantic, but you have to remember to do that. If it's the Earth's moon, then always put a capital letter on it. If it's the moon of another planet, a little m. And then the second answer here, the object that exerts the force. So the object acts on the moon, and the object that's exerting it is, of course, the Earth. So we've got the Earth pulling the moon towards it, and the moon pulling the Earth towards itself. Okay, got a tricky one to end quickly on there, but quick summary. I've got to head off in just a moment. So you should hopefully now be able to give examples of forces, identify contact and non-contact forces, understand the differences between scalars and vectors, and understand how force is a vector quantity. And very last thing I will say is you've got till the 9th of March to use the Tutor 14 code to get yourself a discount for well, take yourself 2 free weeks of the subscription to Snap Revise. I shall say goodbye at this point and thank you very much. And I am going to be back for subscription services from next week. So do get your 2 weeks free, if nothing else. At least join us next week for that. So take care and hopefully see you next week.